All right, today we're going to talk about infinite limits and limits at infinity. So we'll start today by talking about infinite limits. And this goes back to something you've been working with for a while in your math careers. Let's start by looking at these two functions here. Here we have 1 over x minus 1. And we have 1 over x minus 1 squared. And we're taking a look at a couple different limits and see what we get. So the first one says the limit as x approaches 1 from the left. That would be negative infinity. And then the limit as x approaches 1 from the right would be positive infinity. Since those two aren't the same, that means our limit as x approaches 1 does not exist. Look at this graph. As we approach 1 from the left, it's positive infinity. As we approach 1 from the right, it's also positive infinity. So since they're the same, that means our answer is positive infinity. But does that mean the limit exists? It does not. Remember, an infinite limit means the limit does not exist. All right, so going on here, what do limits that produce results of infinity or negative infinity say about the function? Well, let's go back to the graphs here. If we're going up to infinity or down to negative infinity at an x value, it should be pretty obvious that between those two pieces of the graph, we have what's called a vertical asymptote. So, limits that produce results of infinity or negative infinity tell us there's a vertical asymptote in the graph of the function. So you learned about vertical asymptotes in your previous math classes, but now we're talking about an actual math definition of what a vertical asymptote is. And you couldn't learn about this in previous years because you didn't know what limits were yet. But a vertical asymptote is simply when the limit as x approaches c from the left or right side is equal to positive or negative infinity, then x equals c is a vertical asymptote. So in example 2, we're just going to do some review from previous year's math classes of how to find vertical asymptotes. Remember, vertical asymptotes will come from discontinuities in the graph. It will come from infinite discontinuities in the graph, or non-removable discontinuities in the graph. So where do we find those at? We find those in the denominator of our function. So in this problem here, the numerator is not factorable in the real number system. The denominator is. And there's two places where this function would be discontinuous, and that would be x equals negative 1 and x equals positive 1. So it's our job to figure out if those are asymptotes or if they are wholes. If you put negative 1 or positive 1 into the numerator, you will get back 2. So we will get back, as our total function, we'd get back 2 over 0, which is not 0 over 0, which means both of these would be vertical asymptotes. Okay, if there was 0 over 0, remember that means there would be a hole in the graph. Okay, part B, this time the numerator is factorable. And again, we get two discontinuities, one at x equals negative 2 and one at x equals 2. So it's our job to figure out if they are whole or vertical asymptotes. If you put negative 2 into this function, you will get something in the numerator that's not 0 over 0, which means that is a vertical asymptote. So that's good. If you put 2 into this function, you would get 0 over 0, which means there's a hole in the graph at that point, not a vertical asymptote. So that one is not a vertical asymptote. We only have one for this problem. Okay, so read the tip here. It's likely that by now you know that for fairly simple rational functions, finding the location of any vertical asymptote can be done by without actually finding the value c that x should approach to ensure a limit that approaches either positive infinity or negative infinity. Instead, we just reduce the rational function to its simplest form and then set the denominator factors equal to 0. So what does that mean? Basically what it's saying is we could have just canceled this out and then set the denominator equal to 0. And that would be our vertical asymptotes. All right, example 3. Again, we're talking about vertical asymptotes. If we set the denominator equal to 0 here, 2 will never be 0, but x minus 1 will be at x equals 1, and that's our vertical asymptote. For b, let's remember that cotangent is equal to cosine over sine. So really we're looking for when does the sine of x equal 0, right? Well, if we're thinking about just on the unit circle, that would be at 0, pi, or 2 pi, right? But the unit circle is not the only angles possible. We're talking about any pi to the left of 0 or to the right of 2 pi would also be. So how do we write that? You can write x is equal to k pi, where k is an integer. So negative 7 pi, positive 30 pi, whatever. Those will be our vertical asymptotes in the graph. Example 4, find each limit to the best of your ability without a calculator. We can try to make a table of values as we get closer to see what we get. So really, what we want to do first here is we want to put 1 into this expression and get an answer back. But if you do that, you'll get 1 over 0. And since we got 1 over 0, that should tell you right away that, hey, this is going to be a vertical asymptote at 1. So if we're just kind of eyeballing the graph here, at x equals 1, we want to know, is the graph doing this, or is the graph doing this? So what we want to do here is we want to take numbers that are just to the left of 1, but getting closer and closer and closer to 1. So for example, if you put in 0, you would get 1 over negative 1, which is negative 1. If you put in 0.9, you would get 1 over 0.9 minus 1, or 1 over negative 0.1, which is negative 10. All right, and if you still don't know what the answer would be yet, you could do one more. How about 0.999? Or just 0.99, sorry. If we put that in, we would get 1 over negative 0.01, which is negative 100. And at this point, it should be pretty obvious that this limit is going to negative infinity, which of course means it does not exist. But when we're talking about approaching an asymptote, we do like to know, is it going up or down following the asymptote? Same thing's true for b. Again, we're going to get does not exist if we put 1 in. So let's try to make a table here of values from the right. So if you put 2 in, you get 1 over 1, which is 1. If you put 1.1 in, you get 1 over 0.1, which is 10. If you put 1.01 in, you would get 1 over 0.01, which is 100. And at this point now, we should know it's going towards positive infinity, which again means the limit does not exist. But we'd like to know which way it's headed. All right, so let's take a look at the following function, 3x squared over x squared plus 1. So if you have your graphing calculator handy, let's go ahead and put that into y1. Make sure that you put parentheses around 3x squared and parentheses around x squared plus 1. If you just take a look at that graph, see, it looks like my graph, if let's do a really quick sketch of that, would look something like this. Kind of like one of those birds that you drew when you were in second grade, right? And we have a table of values that goes with that, and we're asked to fill in these blanks here below. as x goes to positive infinity, where is y going? Well, look at the table here. As x goes towards positive infinity, y is getting closer and closer to 3. As x goes to negative infinity, it's also getting closer and closer to 3. So this, from previous math classes, is called your end behavior. Right? So as x goes on forever to the left or right, where is y going? In both these cases, y is going towards 3. So what can we say about the limits here? If we converted this into limit notation, we would say the limit as x approaches infinity of f of x is 3. And the limit as x approaches negative infinity of f of x is 3. So these are called limits at infinity. So again, what we did before was called infinite limits. These are called limits at infinity. The concept of limits as x approaches infinity means the following. What happens to y as x gets infinitely large in one direction or the other? We are interested in what happens to the y value as the curve gets farther and farther to the right, or maybe the left. We can also talk about limits as x approaches negative infinity, which is what I'm talking about, is as we go to the left. Okay? The terminology we are used to using here would be limit as x approaches infinity of f of x and limit as x approaches negative infinity of f of x. It doesn't really make sense to talk about approaching infinity from the right. That's not possible. Or approaching negative infinity from the left. That's also not possible. So let's take a look at a couple graphs here and see if we can figure out these limits. As x goes to the left forever, as x goes to negative infinity, where is y headed here? Well, it's headed up. So that would be towards positive infinity. As x goes to the right here forever, y is going towards positive infinity. So the end behavior for this function is positive infinity for both directions. For the second one, as we go to the left, we're going to go up to infinity. And as we're going to the right, we're going down to negative infinity. For number 3, as we go to the left, it looks like we're never going to cross y equals 4. That's going to be our horizontal asymptote here. And as we go to the right, we are never going to cross y equals negative 2. For example 4, as we go to the left, it looks like our graph is getting closer and closer and closer to this line, y equals 1. Remember, your graphs are allowed to cross horizontal asymptotes. They're not allowed to cross vertical asymptotes. And to the right, it's getting closer and closer and closer to the x-axis, which is 0. And our last one, example 5, though, this one, it does not look like it's converging towards any number, right? It's going back and forth from negative 4 to positive 4 over and over again. So we would say that limit does not exist. There's no horizontal asymptote in the graph, and there's no end behavior of positive negative infinity in the graph. And for the right, looks to be the same. It's going to keep going like this forever. But we're not really sure if it levels off there a little bit or if it's going to keep going up to infinity. So this one we would also say does not exist. All right, here's a limits at infinity theorem. And it's pretty obvious theorem, you would say here. If the numerator is 1 and the denominator is infinity, 1 over infinity is essentially 0. As x gets bigger, as the denominator gets bigger and bigger and bigger, then the actual fraction itself will get smaller and smaller and smaller. So as the denominator grows, the actual number will get smaller and smaller. And why is that important? Well, it's going to help us in a couple problems at evaluating limits at infinity. So for example 6, remember what we always want to do for limits is just direct substitution. If we could do that, that would be great. And we can do that here by doing 5 minus 2 over infinity squared, which is the same thing as saying 5 minus 2 over infinity. Infinity squared is just infinity. All right, but 2 over infinity, that number is going to be so infinitely small, it's essentially 0. So it's 5 minus 0, which is 5. So that graph would have a horizontal asymptote as x goes to infinity of y equals 5. All right, here, if you want to do direct substitution right away, unfortunately, you're going to get infinity minus 1 over infinity plus 1, which is infinity over infinity. Okay? Infinity over infinity is kind of like 0 over 0, which tells me I have to do a little bit of work, and I might still be able to get a limit answer to this problem after I do some manipulation. So what you want to do here is you want to divide by the highest x exponent in the denominator. So in this case, it'd be x to the first. You want to divide each term individually by that one at a time. So what does that look like? That would be 2x over x minus 1 over x over x plus 1 over x. So I didn't change the problem because all I really did was multiply by 1. I multiplied by x over x and distributed that, 1 over x over 1 over x, and distributed that through. Okay? Now, if I simplify this, I get 2 minus 1 over x over 1 plus 1 over x. And now if I put infinity in, where I have x's left over, I get 2 minus 1 over infinity, which is 2 minus 0, over 1 plus infinity, 1 over infinity, which is 1 plus 0. Sorry, I shouldn't have that limit there, which is 2 over 1 or 2. So example 8, we have 3 rational functions here. And they all look very similar with one small change. The power in the numerator changes. All right, so we're going to do all 3 of these in the same manner, and we're going to see what we get back. All right, if we want to put infinity in, we can't because we'll get infinity over infinity. So we'll need to divide all of these by the highest power in the denominator, which is x squared. So 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. All right, and if we simplify this a little bit, this would be 2 over x. And that would just be, that would just be 3. And now if we put infinity in, we would get 0 plus 0 over 3 plus 0, which is 0 over 3, or 0. Now the second problem here is going to be done in a very similar fashion. The only difference here is that we have a squared right there. So when I divide 2x squared by x squared, I get 2 here. When I put infinity in this time, I would get 2 plus 0 over 3 plus 0, which is 2 over 3. So that's our limit. The third one is, again, almost the same. The only difference is we're going to change that squared in the numerator to a cubed in the numerator. So when I simplify this, I get limit as x approaches infinity of 2x plus 5 over x squared over 3 plus 1 over x squared. And now if I put in infinity, I get infinity plus 0 over 3 plus 0, which is infinity over 3, which is infinity, or it does not exist. All right, so a couple of questions on here. Would it make any difference if infinity was negative infinity? No, it would not. Okay? And our question is, do you remember this shortcut for knowing these answers from pre-calc? And I hope the answer is yes to that. Okay, let's take a look at the shortcuts. If the numerator's degree is less than the denominator's degree, the limit is 0. That was the first example A. That's the horizontal asymptote. We learned last year in pre-calc. If the numerator's degree is less than the denominator's degree, the horizontal asymptote is y equals 0. The second one, if the numerator and denominator both have the same degree, then the limit would be, well, I usually say m over n or a over b, whatever that is. But what it is the ratio of the leading coefficients. So going back to our B problem, you see our leading coefficients are 2 over 3, and that was our limit. And then the last one, if the numerator is greater than the denominator in degree, the limit of the rational function does not exist. It's going to go to positive or negative infinity. Okay, and if you also remember from pre-calc, if it's 1 greater, so if the numerator is 1 greater than the denominator, you would get what's called a slant or oblique asymptote. If it's more than 1 greater than, you would not get a slant or oblique asymptote. All right, example 9. A function where the two results differ from positive and negative infinity. Let's take a look here at what this would look like. So you want to put infinity in here, you would get infinity over infinity, which is not going to work. So we're going to have to do some manipulation with this. All right. So we're kind of thinking the same thing here. I'm going to do the denominator first. You want to divide each term by individually, like I said, the highest power of the x in the denominator. So this would be 2x squared over x squared plus 1 over x squared. However, we're not really dividing by x squared because it's a square root of x squared. So really what we're dividing by is x or negative x. We got to figure out which one that is. Because we're going to positive infinity, we're dividing by just positive x. So in the numerator, I'm just going to divide by positive x. And then that gives me, limit as x approaches infinity, of 3 minus 2 over x over root 2 plus 1 over x squared. And now if I put infinity in, I get 3 minus 0 over root 2 plus 0, which is 3 over root 2. So that is our limit. But this problem actually does differ if you go to negative infinity. All right, so I'm going to copy this over here. My first step is almost the same. What's different about it? Well, this is negative infinity, right? So when we go to negative infinity, the square root of x squared would be negative x. Because negative x would also give you x squared. Negative x squared would also, if you have negative x parentheses squared, you would still get x squared. So we're going to divide both of the top terms here by negative x. So now I get limit as x approaches negative infinity of negative 3 plus 2 over x over, and my denominator is going to stay the same here, 2 plus 1 over x squared. And now if I put in infinity, I get negative 3 plus 0 over root 2 plus 0, which is negative 3 over root 2, which is the same numeric answer, but the opposite sign of what we got for A. So a problem such as this, you could get two different asymptotes for your graph. So I've been saying horizontal asymptotes the whole time here, and that's really what we've been doing, okay? Last year you learned how to find horizontal asymptotes. Now we're actually proving it using calculus. The line y equals L is a horizontal asymptote if, as x approaches infinity or negative infinity, the function goes towards L. Okay? So, if we take a look at problem A, we can do this using our pre-calculus methods or our calculus methods. It says determine the equation of the horizontal asymptote, if any, of the graph of the function. So using calculus methods, we can do the limit as x approaches infinity or the limit as x approaches negative infinity of this function and divide by x squared, divide each term by x squared, and then put infinity in. However, if you know your pre-calc methods, since the denominator is higher, we know the horizontal asymptote is at y equals 0. So if I did do the limits, I would get 0 on either side as x approaches infinity or negative infinity. So here's where the pre-calc shortcut can come in handy. For part B, because the degrees are matching, we know it's leading coefficient over leading coefficient. So 4 over 2, our horizontal asymptote is y equals 2. If we did the limits, as we approach negative infinity or infinity, we would get 2. Here's the only difference here. This one does not exist. So we may want to know there's no horizontal asymptote, but you may be asked, is it going to positive or negative infinity? So you would have to do that process of dividing each term by x squared and then putting infinity or negative infinity in and seeing what you get back. Okay? But if we're just asked for horizontal asymptotes, we know by looking at this, there's none because the numerator is higher than the denominator. All right, so example 11 says finding horizontal asymptotes. Determine the equation of any horizontal asymptote, if any, of the graph of the function below. So at this point, we know that we can do this. We can't do this using pre-calc methods because we don't have the powers to look at this, but we do have our calculus methods where we can do the limit as x approaches negative infinity of this function and a limit as x approaches positive infinity of this function. All right, now what we're going to do is we're going to divide by, in the denominator, we're going to divide by x squared inside the root. And the numerator, since this is negative infinity, we're going to divide by negative x. So it's going to be 8x over negative x minus 1 over negative x. And for this one down here, it's going to be the same thing, except since we're going to positive infinity, we're going to divide by positive x on both those sides there. Okay, and then we just do some simplifying. So we would get limit as x approaches negative infinity of negative 8 plus 1 over x over root 2 plus 1 over x squared. All right, and this one down here is the same thing, except we're going to have positive 8 and then minus 1 over x. And if we put infinities in where they belong, we would get negative 8 plus 0 over root 2 plus 0, which is negative 8 over root 2. And here we would get 8 minus 0 over root 2 plus 0, which is positive 8 over root 2. So our horizontal asymptotes would be y equals negative 8 over root 2 and y equals 8 over root 2. If you wanted to simplify those radicals, you would get plus or minus 4 root 2. Example 12. Determine the equation of any horizontal asymptote, if any, of the graph given below. All right, so if we had a limit as x approaches negative infinity of sine x over x. There's no real way to do this besides thinking. All right, the numerator, we know we're going to get some number that's between 1 or negative 1. And the denominator, we're going to get a huge number, right? As we get smaller and more towards the left side, more closer to negative infinity, we would get a large negative number. So really what we're going to get is some really small number between -1 and 1, c, in the numerator, and then a number with a very big numerical value in the denominator. But it's negative, so it's negative infinity. So we have a constant c over infinity, and that would be 0. And if you want to take a look at this at the other side, limit as x approaches infinity of the same function, the thought process is the same, except we would have c over positive infinity, which is still going to be 0. So this is another one of those limits that you probably should commit to memory. Limit as x approaches positive or negative infinity of sine x over x would be 0. Which brings us to our last slide. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions. So just take a look here. It's not going to be a, as we have a way to converge that. We have a way to work with that. But it's not going to be a. B is a line with a slope of 5, so it's going up forever. C, we know since the denominator, it's bottom heavy, we know it's going to go to y equals 0. D, since the degrees match, we do coefficients, that would be 5 over -1. So that'd be -5, so that's not right. And E, the degrees match, so we do coefficients, and that would be 20 over 4, and that one is 5. So our answer would be E. Y equals 5 would be the horizontal asymptote of that function. What are all the horizontal asymptotes of the graph 5 plus 2 to the x over 1 minus 2 to the x in the xy plane? So what we're going to do here is we're going to do limit as x approaches infinity of this function, and then we'll also do limit as x approaches negative infinity of this function. Okay? If we put infinity into this, we would essentially get 2 to the infinity plus 5, but when you're at infinity, adding 5 isn't going to do much, over -2 to the infinity, again, plus 1, but again, that's not going to do much. So 2 to the infinity over -2 to the infinity would be -1. So one of our answers is -1. And now we're going to do the same limit as x approaches negative infinity. Let's see what we get back. So that would be 5 plus 2 to the negative infinity over 1 minus 2 to the negative infinity. All right, and that would be 5 plus 1 over 2 to the infinity over 1 minus 1 over 2 to the infinity. And these are essentially 0. So we get 5 over 1, which is 5. So the answers are y equals -1 and y equals 5, which is, again, E. And the last one, which is a very similar thought process to that, I'd like you to pause the video there and try to work that one on your own. And when you're done, come back, and I'll go through the answer to that one. So hopefully after working through, you got our answer to be D, y equals 3 and y equals 7. That'll do it for today's lesson, talking about infinite limits and limits at infinity. Thanks for checking in today.